So welcome back. Now we're talking about the last topic, and this, of course, polar codes. Polar codes are, of course, an information theorist dream for several reasons. One is that it's the only code I know of where things like mutual information, conditional entropy, not only tell us what the boundaries are that we achieve, but these play a fundamental role in the actual construction, right? So if you look at the proof and so on and of the achieve, directly in the proof for the specific code, these are the quantities that really matter. The other reason they're a dream, even better, is that if you're an information theorist and let's say you were asleep the last 60 years, never looked at coding, within 2 hours you're up to date, okay? And so when does that ever happen, okay? So that's very nice, also somewhat embarrassing, but that's how it is. Now, this is, of course, our next hero here, Erdal. And this is another picture. This is a picture from taking it at ITA. Okay, you can't really, it's a little bit dark here. Another one, this is David Say. You might know this person here. What do these two people have in common? These two. This, I don't know. And this. I claim that they both like patterns, okay? So it's unfortunately a little bit dark. Good. Now, just Jack told us that you can make billions with constraint coding and in magnetic recording. Polar cards are not quite as ambitious, but you can make something like 2.5 million here. Okay, and this was a big grant that Erdal got according to the translation of Emre, okay, to work on polar codes. So, there's also money to be made in coding, okay? So if you need any more motivation. Good. Now, I assume many of you, of course, have heard about polar codes, but since it's a mixed audience, I want to spend a little bit some time on it. I'm not sure it will be, of course, slow enough that if you've never heard it, it will be enough. And of course, for those that have heard it, there will be some kind of repetition, but I don't think you can avoid that much. So let me just give you a 10-minute or 15-minute tour of polar coding. And then at some point, I will, when there's something that we need, in particular about some scaling, I'll wake you up. Okay, at that point, I'll tell you when there's something that we'll need later on. So how do polar codes work? Well, we take a matrix. Everything is GF2 in here, 1, 0, 1, 1. And we take successive Kronecker products, which means whenever there was a 1, we replace this 1 with this base matrix itself. And in this way, we get a sequence of matrices of increasing length. And of course, the dimension of the matrix will be now n is 2 to the number of steps, which in this case is called m. So 2 to the number of steps will be the size of the matrix. Now, once we have a binary matrix, we can think of using this binary matrix as a code, right? And I can think of this, let's say, as a generator matrix. This is my information. That's the matrix. That's the code word. And this matrix itself, or this multiplication here, can, of course, be modeled or can, of course, be represented in terms of a graphical model here. So, for example, if you look at the last column here, right, if I multiply this with the vector, I get U7, right? So here I see, here I see that X7 is exactly U7, right? That corresponds exactly to the 1 here. And then if I look at these columns here, I see that that X6 is just the sum of U6 and U7. That's exactly this. And I guess it's not surprising, given that we had this nice recursive construction, that this matrix here has a very nice structure. And even though we won't say much about it, it's perhaps not surprising that this structure is here, that it has length n here, and that the depth of this thing is log n, which is exactly the number of steps. So when later on we'll just quote some complexity results, they will all come from the fact that this will think of this as like a factor graph, and the number of edges and nodes and so on, this is all proportional to n log n. Now, if we had it like this wouldn't be very useful because this is a one-to-one map between something of 2 to the m and 2 to the m. But we can make it into something useful if we, let's say, selected a subset of the rows. And so once we select the subset of the rows, there are several ways we can think about it. I can either really just delete them, or I can do something equivalent. I can simply set some of these components here to 0. Okay, so it's an equivalent way of thinking about it. And so I can, in the same way in the graph here, I can leave the whole graph, but simply set some of these inputs here to 0. They will simply play no role. Now the question is, what should I do? Which of these rows should I set to 0? And so let's say in classical coding, the answer would be, well, pick those rows that have largest weight, because even though the weight of or the minimum distance of a code is not just given by the minimum weight of the rows in the generator matrix, at least starting with something that's large is a good starting point. If I start with something that's very low, clearly I will not be able to have very high minimum distance. So let's assume I pick in this case the ones that have the largest number of ones, and these would be cases that have weight 4 or 8. And indeed, that's a very well-known code, and this is called Ruediger code, and has been studied extensively for quite a while. Okay, but this is not how polar codes proceed. Polar codes start with the same matrix, but they pick some slightly different set of rows. And so we need an extra concept here, namely a concept of successive decoding. So let's think of the following here. So let's think of now, we had here my input u's, then I have my output x's. So I'm putting here some u's, I get some output x. This was just the encoding we saw before. And now let's assume I send it through some channel, and let's assume these are all the same types of channels. Think of a Gaussian, a BSC, BSC, whatever you want. And now let's think of the following set of channels that we can construct from them. So first think of the first bits here, namely the U0. And so think of that all the bits here, namely think of these as bits in the future that you don't know yet. Think of them as just being randomly chosen, 0, 1, equally probable. Then there is, of course, a channel here between U0 and the whole output here, y. Okay, so we have a channel between U0 and y. And this channel will have a certain capacity, and we denote this channel here, W. This is the n for the total length of the code that we have, and this is channel number 0. Now, once I hopefully, so let's assume I send something for this channel, and hopefully I do this in a smart way such that I can actually decode U0. Now, at that point, U0 is actually known at the output. So what we could now think of is that think of the channel U1 with, again, all the bits here in the future as noise. But now I know actually U0. So now I have essentially effectively a channel between U0, y, and I have a condition U0. But U0 and U1 are chosen independently, so that's the same as U1, and then I have output, I observe y and U0. Okay, again, this is a channel, has capacity. Hopefully, I have a scheme over which I can transmit over this channel, and hopefully, I can do it such that I can recover U1. And so clearly, you see that I can go on and have a sequence of channels. And again, if I started with an n system, so n inputs, n outputs, then I get n different channels here. Where every time I assume that I know I've decoded the previous part perfectly, but don't know anything about the future. Okay, so now the miracle of channel polarization is that if I do this for large n, that this set of channels will polarize. That's exactly what gave rise, of course, to the name, in such a way that if I randomly picked one of these channels here, I would either find that this channel is essentially a useless channel, so has capacity very close to 0, or is a channel that has capacity essentially 1 and is essentially a perfect channel, right? And that's, of course, very good news, because these are the only two channels over which we actually know how to code, without, with much effort, because we simply either not use it at all, or we simply don't need to use coding whatsoever. Okay, so that's, of course, the idea. So the idea will be now that so there's one extra thing that I didn't mention. We can also, another thing, it would be one thing if they just go to 0 and 1, but what is if all the channels would be useless? Okay, that of course wouldn't be very nice. Well, just by the chain rule of mutual information, you can actually see very easily that the total capacity is here preserved, so the fraction of channels that will become perfect channels must be exactly the correct fraction, namely must converge to the capacity. Okay, so now what is then the scheme? The scheme will be is that I pick a very large n. I determine which of the channels are good or bad by some procedure. I pick those channels that are bad. I simply set those values to 0. I'm not using them. And for the remaining channel, I simply transmit uncoded, essentially. Okay, so that's exactly the polar codes in 5 minutes. Okay, so let me just repeat this, maybe just to to C again. So let's assume I decided that in this case, U0, U1, U2, and U4 were the useless channels. So these are what's sometimes called the frozen set, those channels that I don't use. The bits that I'm actually using is U3, U5, U6, U7. Now I have 4 input bits. I have 8 output bits. So this is a code of rate 1/2. And so what I will simply do now is simply put my information directly here, which corresponds to uncoded transmission of information. And the rest, I don't transmit anything. So I go from 0 to n. And for each of the bits in succession, I simply assume that I know the bits before and I decode. And so in this case, the first 3 bits I know because I have set them to 0. So the first bit that I need to decode is bit here U3. These bits I know, they were 0. This is by definition. I compute the map rule here. And because of the special structure of this code, this can be done efficiently. This has the total complexity is n log n. And then I simply make a decision based on the likelihood here. And I continue on. And hopefully, if at no point I made a mistake, I will have decoded the whole code word. And as I said, the complexity will be n log n. OK, now that's great. But let's see now a little bit more in detail how these things perform. So we know that, let's assume we believe even that asymptotically these codes achieve capacity, as Erdal indeed proved. Now, let me first give you a small demo. If you want to go to a web page, Stefan Meyer, a student, programmed a nice applet. You can try various lengths. So this means you have a particular code here. This is length 16. You at some point decided on which channels are good and bad. Now, this is the quality of the channel. 1 means terrible. OK, so this is what's called the Bhattacharya constant. 0 means very good. OK, Bhattacharya constant is fairly, you can bound fairly closely with respect to the error probability. So, you might as well think of it as the error probability roughly here. And so you can see these are good channels. These are terrible channels. So sort these channels by the Bhattacharya constant, for example, and pick the worst ones. Let's say you want the rate 1/2. Pick the worst ones and map them to the frozen ones. Pick the good ones. Put some set of information here. Through the transform, this gives you a code word. Let's say +/-1. This is a binary additive white Gaussian noise channel. You send it through the channel. This is the received word. And then now you do the decoding according to this rule here. So this is done actually, if you go through it randomly, it will give you different outputs. And in this case here, we are lucky. It actually decoded. No, actually, yeah, I don't. OK, so it decoded these actually, I think, correctly. OK, so in this case, we're lucky, and it worked. Good. Now, how well does this work? OK, so let's, we kind of think of now, we're not talking directly of this scaling yet, but we know that as we do more and more iterations, we're saying that these channels will become either good or bad. And we'll talk a little bit more about this process here. But let's just empirically see how this works. OK, how well does this work as a number of steps of iterations? And so again, this is an applet. So you can choose your channel here. And then, so typically they are set. So these are all essentially rate 1/2 channels here. And so this will be the block length. OK, so this will be the m is the number of steps. And so, for example, if you have 2 to the 2, then it means you have only 4 channels. OK, and what this thing plots you is essentially the Bhattacharya constant of the various channels. So this is the best channel. So it sorts it. So this the best channel has this Bhattacharya constant. And these are the 4 channels that you see here. OK, and so now essentially, since they go up here, typically fairly rapidly, the way we will think about this is that when you do successive decoding, so there's 2 ways you can bound the error probability, upper and lower bounding in just a trivial way. And this will be enough right now for us. The error probability cannot be better than, let's say, the worst channel that you have picked. OK, so if you pick, let's say, you include a particular channel I, this has a certain error probability condition that everything else so far has been correct. Clearly, the error probability will be at least as large as that, right? But it can't be worse than the sum, of course, of all the other ones, just by the union bound. And you can sandwich this in between these 2. Typically, these things are fairly rapidly decreasing. So these bounds are actually not too far away. OK, so now let's go a little bit larger. Let's see how this behaves. So every time you do a factor 2, you can see here, right, the length goes up. And you can see here that indeed these things will become steeper and steeper, right? And so now we have reached a length 1,000,000. And so now you can no longer see the individual points. But what this means is the following. If you wanted, let's say, a target bit error probability of a block error probability here, I guess it's block here of 10 to the minus 10, then wherever this thing hits here, that's essentially the rate that you can achieve. Okay? So this one would be for a rate a half code. So the threshold would be, the channel is such that the capacity would be a half. Okay? So the threshold would be 0.5. And this is whatever, 0.42 or something, or 43, I don't know exactly. So this is still, you're still a little bit away. And indeed, later on, we'll look a little bit more in detail to see, we're exactly interested in, if we're now sitting here and we're looking at larger and larger values, we want to see how fast does this actually approach the limit here, right? That's exactly the scaling that we are interested in. OK, so now just maybe in a little bit more detail, how do these things polarize? Well, the basic, essentially all you need to know or all you need to study is one step of this polarization. So one step is exactly if you take two channels that are the same and you do this combination here. This corresponds to the base matrix 0, 1, 1, 1. And you send this through the channel and you have the output. And the two channels that you create from these two independent ones are the following. One is you're taking bit U1. And you have as output y1, y2, given that that's noise. And so this means you have u1 is, so if you think about this here, what is x1? If you just rewrite the relationship between u1, x1, and x2, you will see that u1 is x1 plus x2. Okay, and then you observe y1 and y2. So this corresponds to the following. I have two bits, x1 and x2. I send them through two independent channels. I get observations y1 and y2. And the variable that I'm interested in is the sum of the two. Okay, so I want to estimate u1, given that you have the observations y1 and y2. And if you looked ever at iterative decoding, right, that's exactly the operation that you have at a checksum. Okay, so it's exactly, you have two independent inputs here, and you look at the output here. That's exactly what happens at the parity check node. And on the other hand, you have the channel U2. Now you know U1 here. So now what do you have? You have that U2 is equal to X2. Okay, so this is simply whatever comes in here is that. And on the other hand, you have that U2 is also equal to X1 plus U1. Okay, and so essentially, U1 is just a fixed constant. So think of U1 as 0. You know it's just a fixed shift, the translation of it. So it means that essentially, if you took this away, you would have the bit going through here, and you have the bit also going through here. Okay, so now this means we have one and the same bit that we send for two independent channels, and we want to estimate the bit. That's exactly the same thing what happens at a repetition code, right? So you have some bit x2, you have a bit x1, but this is just the same as the previous one, shifted by some predictable constant. So let me just call it x1 here. And you have two independent observations of these bits, and you want to estimate U2. OK, so now to make it simple, what would happen now in this transform if you looked at the binary erasure channel? Well, let's assume you had two observations here, and they have an erasure probability epsilon, right? So what's the erasure probability of this bit here, okay, which is the sum of the two, right? Well, it's exactly one minus. So it's this will be erased if any of the two are erased. Okay, so if either this or this is erased, then this bit will be erased. Okay, and that's exactly the probability for this. And that's of course worse than just the probability that a single bit is erased, right? But on the other hand, if you go on the other side, what's the probability that you have two bits that have each erased with probability epsilon? And this bit will be erased only if both of them are erased, right? Which happens with probability epsilon squared, right? Only if both of them are erased, then you get probability epsilon squared. And so now, so you have now two different. You started with 4 BCs with probability epsilon. Now you ended up, you should divide it. But now you ended up with two channels, one like this and one like that. So what happened to capacity? Well, the first channel has capacity 1 minus that, which is this. The second one has capacity 1 minus epsilon squared. And if you sum it up, you'll see that indeed you get 2 times 1 minus epsilon, which is exactly twice the capacity of the original channel. You use 2 channels to create 2 new channels, and the sum capacity indeed stayed the same. So it's not very hard to see that indeed the same thing is true for the general case, that the sum capacity stays the same. But exactly what makes polarization happen is, of course, that you started with a value epsilon, and you get one value which is worse, and you get one value which is better. Okay, and that's exactly the polarization process, and we'll look at it in 2 minutes. We'll look at a little bit more in detail. So what you should remember right now, so that's the time to wake up, we will see the mapping again. We'll see the mapping epsilon goes to either epsilon squared, or epsilon goes to 1 minus epsilon squared. Okay, so this mapping we'll see quite often. Good. So now this is just some empirical, just to see this again, just a different way to see essentially the same thing. You have 2 channels, let's say, with erasure property epsilon. You construct 2 of them. 0.5 will go to the 0.5 squared, which is 0.25. And since we know that the sum is equal to, must be preserved, this must be 1 minus 0.25. You do this now again, one step. You'll see that 1 becomes much worse, has an erasure property of almost 1. But you see that already the first channel becomes much better, and then you have 2 somewhat in between. And you go on, and you see that now you have some already pretty good. This is almost 1. So you see already the first kind of remnants of this polarization. OK, so just maybe a little bit to the history before I then talk about the specific things. Now, of course, the big bang here is Erdal's paper. And then there was some important work by Erdal and Emre about the exponent. I'll talk a little bit about this. There's work about source coding, non-symmetric, non-binary channels. There's thing about the multi-axis channel, so you can do the same kind of polarization directly on the multi-axis channel. There's lots of interest in the wiretap channel, and indeed people have shown that you can build secure codes for the wiretap channel. There's work on specific constructions. How do you find these good and bad sets? And I'll talk a little bit about the scaling approach, and I'll tell you a little bit about this. So there's lots of interest, and I'll tell you a little bit later about what are the kind of the open questions and what might be interesting to work on. Okay, so let's now look again at our 2 problems. The first one is an error exponent. Well, so it's not exactly an error exponent because it doesn't scale like e to the minus block length, but slightly different. But how does it behave for very large lengths? So what's the equivalent of the error exponent? Well, let's first have a first guess. Okay, we'll just do a very rough idea how this works. So remember, right now I wrote it as z before it was epsilon. So think of z here, and the reason we write z is because for the general proof for channel channels is very similar. And z is the Bhattacharya constant, which for the erasure channel is exactly the same as epsilon. Okay, so if you don't like to think of Bhattacharya constant, just think of erasure probabilities. If you know what a Bhattacharya constant is, then just think of the Bhattacharya constant. So for the erasure channel, there's 2 choices, right? So one way we can think about this channel splitting is that we have this large tree, and we can think of we start at the root, and then I can either go to the left or to the right, and I do it with equal probability. If I go to the, let's say, left, the z goes c squared. If I go to the right, the z becomes 1, becomes this other one, 1 minus c squared. Okay, and so I can think of now picking a random channel from at the leaf is the same thing as simply walking down the tree at any point in time, either going left or going right with probability 1/2. Right, and so I'm following now this means I have some stochastic process, which at any time step I either do this step or I do this step, and we want to know. What is now the distribution on the bottom, right? That's what we're interested in. Okay, so one way to write this is just to write it like this. So we say it's c squared and it's 2c here. Okay, so take, as a first step, just take y is minus the log of z here. Then this becomes c squared here becomes just 2y, right? And so here, if I'm thinking about it, so this I just bound here by y minus 1. In particular, what we will think about in a second is we'll think about, since this is something what happens after many time steps, we think about what happens after z has already become relatively large, small. Okay, so z is maybe already 10 to the minus 3, right? Then what will happen is that either I get here c squared, which is 10 to the minus 6, or I get essentially 2 times 10 to the minus 3, and then something that's even much smaller here. Okay, so as a first thing, let's just essentially we'll ignore this part here. Okay, now take the log again, then we'll get here a 1 for this, so we get x goes to x plus 1, and I just ignore this part here, and either I essentially stay where I am, or x will become 1 larger. Okay, so it's of course an approximation because we forgot about this term here, but as a first estimate, what would happen if we had exactly this process here? Okay, so what would happen with this process here? Okay, well, if we're looking at this process here, then this is just like a random walk, right? So let's assume I start at 0, and at any point in time, with probability half, I go either 1 to the right, and with probability half, I stay, right? And now you do, let's say, m steps. Well, what will happen after m steps? Well, in expectation, you will have done m over 2 steps to the right, right? Because with probability half you go. And then, of course, you have some small distribution around it, right? So if we're assuming that I did essentially m over 2 steps, then what would this mean? If I now go back, remember I took twice the log, right? So this means it's m over 2. It's 2 to the m over 2 for the y process. And if I go to the z process, it's 2 to the minus 2 to the m over 2, right? But 2 to the m was the n, was the block length. So 2 to the m over 2 is the square root of the block length. So this means that what I should expect, if for this process, you know, just like this, I should expect that it's 2 to the minus square root of n, right? Okay, so now you can say, well, okay, fine, but you know, we took this thing out and so on. But it turns out that indeed this is correct, okay? And this was Hamid Hassani. So the first proof with this without the extra term here was given by Erdal and Emre, who showed something equivalent. So essentially they say the probability that this is smaller, and now what is the right scaling? It's exactly the 2 to the minus 2 to the m over 2, okay? That this probability here, they had a result saying that if you take a scaling here which goes down less fast, then the probability here will go to 1, okay? And now this is slight refinement, which not just says this, but it says that the right scale to look at it such that you get a constant is here that you have an extra term. And again, we see a scaling of the form with square root of m, something very similar than before, okay? So, you know, the details are not so important here. What it says is roughly the block length eventually, for very large n, will go down to like 2 to the minus the square root of the block length, okay? So it doesn't have an error exponent in traditional sense because this would be 2 to the minus block length times some constant. But it's still, you know, pretty good, right? If you take large lengths, this still would be, of course, very, very small number. Okay, so that's the error exponent. But now let's look at what happens for the Bhattacharya, or what happens for the scaling, right? Because typically we know that the scaling is really the part that's the more relevant one if we're talking about finding codes that have a certain fixed probability of error. Okay, so we're still going to first look at the BSC. So we're looking at the Bhattacharya process. It's still the same process here. Now, so what happens, right? So I have my axis, and I start somewhere on the axis, and let's assume at a point z. Well, okay, so what we said, with probability half, I'm going to go to z squared, and with probability half, I'm going to go up to this point here, right? So now, to make it simpler, okay, so you can do the same thing with different parameters. Let's assume that the epsilon we start with is a half, okay? This just symmetrizes the whole problem. So if epsilon is a half, then the whole problem will be symmetrized. You can rescale and get other things where epsilon is not a half, but we'll stick with this formulation because it's slightly easier. Okay, so so this means I start the process with a point here, and then with probability half I go here, or with probability half here. Then for each of the 2 points with probability half I go here or here, and the same thing here and here. So I have now 4 points, and then I have 8 points, and I have 16 points, and I'm looking, you know, this is eventually how the process behaves, right? And so now I'm interested in the scaling. So what does this scaling mean? Well, what I will be interested in is I'm going to look at, since things are symmetric, I only have to look at 1/2 parts. So I'm going to look at the bottom half here. I'm going to look at how many of the elements lie here in some region here, right, between a half and the point here, right? Now, I'm going to call this quantity Q. N tells me of how many points I have currently in the system. And in order so that this formulation also makes sense for the general case, let's look at the error probability. Okay, so for the erasure channel, the error probability is exactly twice the, the error probability is just half the erasure probability, so there's just the scaling between the two, right? So I could just, if something is erased, I can just guess it with probability a half, okay? So that's why we have here a quarter rather than, so this is Bhattacharya here, which is erasure. This is error here, and so there's unfortunately this factor half. So this goes from not to a half, but to a quarter. And then if I have here an x, I actually see here 2x, okay? It's just the scaling between erasure probability and error probability. And the reason to do this is because this formulation then also makes sense in the general case. So I'm going to be interested in how many of these points lie between a point z, which is 2x, and the point a half here, right, under this process. Okay, so now I guess you will not be completely surprised to say that if I tell you exactly this function here in the previous slide, okay, so if I tell you exactly this distribution here for all x, right, for some n, and if I do one extra step, I guess you will not be surprised that because this is just an explicit map here, that there should be a relationship to what the distribution will look like in the next step, right? Now, okay, so presumably that's this, okay? Now, the exact formulation is not so important. All we need to convince ourselves is that I tell you exactly the distribution. So essentially, I tell you exactly what these points are, right? And so now, of course, once you know where the points are, you will know that after one further iteration, also where these points are, right? And the question is now, how difficult is to describe this map? And it turns out that if you look at the q for twice the length with the x, then you can relate it to, in this way, to the q's that you had for length n. Okay, so this all depends on length n here. And so, okay, so there's slightly some ugly minimum and so on, but okay, fine, right? So there's a formulation. So now, for polar codes currently, we cannot really prove that there's a scaling of the form, so we have to make some kind of assumption. So we will assume that there's a scaling of the form, and that's the following scaling assumption. We will assume that indeed, if you looked at this distribution here, so you look at how many points end up between some x and a half, okay, that this number here, properly scaled by n to the sum 1 over mu, that this number will converge to something. Okay, that there's a limit, and this limit we call q of x. So just to make sure that we understand that, the total number of points I have in the system is exponential, right? Is 2 to the m, right? Now, most of them we know, of course, will go to the boundaries, will go to 0 or 1, right? But it's not true that there are no points in the middle, right? Indeed, there will be an exponential number of the points in the middle, but the exponent is less than the exponent on the outside, right? So there will be essentially 2 to the m points on the boundary, and there will be some other, not 2, some other exponent, okay, alpha to the m points in the middle. And this exponent will be smaller, right? But there will still be an exponential number in there. And so by scaling properly, so if we could guess how this scales, right, then we might hope that this indeed goes to a limit, right? So we'll make this assumption here. Fine. So if we do this, then according to this, now let's think of, so now what we then think of is that we're now going to replace this with this scaled versions here, okay? So let me just take this equation here, but I'm going to plug in here now, forget even about the limit, okay? Who cares about the limit? I'm just going to plug in this, and I plug in this scaled version here. So I'm going to replace, so I can write qn of x is n to the minus 1 over mu to qx, and that's what I'm going to plug in here. And then I'm going to clear the terms, and I'm going to get this functional relationship here, okay? So assuming that there's a scaling of this form, right, then this is the mother curve, remember, then this mother curve should follow this functional equation, right? And so now, if you have such a thing, then of course you can solve it. Functional equations of this form, I don't think there's necessarily an analytic solution to it, but you can easily solve it numerically. You plug in some value for this q. To start with, you run for once with recursion, you plug it back in, and you just do this, and you cross your fingers that things actually converge, okay? And so there's some ways to actually make sure that things converge. And so if you do this, you will get this limit function here, q of x. So that's our mother curve. But you don't just get this q of x. You will also find out, if you do this correctly, what actually the mu is, okay? So there's a way of solving this to find the mu and the q of x. And if you look at this equation in here, this equation is underdetermined in the sense that if you multiply everything by a scale factor alpha everywhere in here, a solution Q of x, you multiply everything by alpha, this will still become a solution. Okay? So there's one parameter that you don't know out of this thing. And so this means you need to somehow arbitrarily rescale it. And how do you rescale it? Well, maybe you picked some point here, for example, the point here, whatever this point here is, an eighth, and you simply fix the parameter. You say that I require in the recursion that this parameter is here 1. Okay, so there's some parameter that you don't know. Okay, so now we made an assumption, right? We made the assumption that there was a scaling in there. And indeed, one of, I think, a nice open problem would be to see that, indeed, to prove that this is true. But we can at least check it, right? We can check whether or not we get meaningful predictions. And so when we do this, we can do this for the BEC. We get that the mu is about 3.62. And assuming that you have a scaling at all, you can actually give, so you can give actually analytic, not numeric, but you can give analytic upper and lower bounds on the mu by various formats. It has been done by several people. And the interesting thing is that the mu is not the same for various channels. So for example, for BEC, you get about 3.62. If you do a similar procedure, it can't be the same because it's more complicated, but if you do a similar procedure for the Gaussian, you get that the mu is very close to 4. Okay, so important thing is, number one, depends on the channel. Number two, mu is much larger than we had for the case of all the cases beforehand. Okay, so roughly, if we think of the Gaussian, it's roughly a factor 2 larger, and we'll get back to it because this will have important consequences. So now we can check this, right? So again, we can use a scaling law as prediction as beforehand, and so so this means these are actual curves that you can do for lengths 223, 224, 225, 226. So these are the actual, you can determine them exactly. You can rescale them according to the scaling law here, and you see that indeed, at least numerically, this fits. Okay, so there's no question in my mind that this is actually the right scaling law here. So now an interesting and challenging open problem would be to prove that that's indeed true. Okay, good. So now let's get back now. So presuming that we believe that this is indeed the right scaling law here, let's check what we can say about our problem here. So remember, we had here this case where we had 2 to the 20 million, and we were here, and so I just roughly, this is roughly 0.43 bits, and the capacity of this was a half, so this means we have roughly 86% of capacity that we hit here at 10 to the minus 10, right? And so now what would be our prediction? How long, how large a length would we need, according to the scaling law, to get, let's say, within 1% of capacity, okay, at 10 to the minus 10, just arbitrary numbers? Well, we can do exactly what we did beforehand, right? So again, this fixes the error probability, so we fix the z, we have the delta, so this means n goes to z delta over to the mu. So now we can figure out how much delta has to be in order to get 1% of capacity, right? And we take this delta, and then now we have to take this delta to the fourth, roughly to the fourth power, right? Because we said for this scaling, it's the fourth power. And if you plug this in, you will see that for this particular case, you will roughly need about 10 billion to get within 1% of capacity. Okay, and indeed, you can also check that for the scaling. You can check here that whatever we did beforehand is correct. So this is exactly, I guess, one of the problems currently that polar codes have, right? I mean, has been observed, of course, repeatedly that if you're thinking of putting polar codes currently directly on a chip, okay, the only thing preventing from doing that is exactly this, okay? That now this is one particular case, and you can do this for the BEC, you can do this for Gaussian, etc., which is even worse because the mu will be even larger. This is actually computed with 3.6 and so on. The problem is right now that polar codes, unfortunately, the scaling is relatively slow, right? And that's not completely surprising, because if you think of this process, right, you have this stochastic process, things will go either to 0 and 1, right? But now it's clear that some of them, if you're lucky, you go like c squared, c squared, c squared, you're very close, very quickly to 0. But I'm not interested in how the fastest guy scales. I'm interested in how the worst guy scales that I include, right? And so until the worst guy really gets close to 0, that unfortunately takes a long time, okay? So I'll mention it a little bit later again, but I think so I think there are two paths in polar codes that to me sound very interesting. One, try to find a way to somehow modify the construction to get polar codes which scale a little bit better than that, okay? 2 can use polar codes, of course, for, we mentioned before, in all kinds of channels. For many of these channels where you're not expecting to put this polar code directly on a chip, but where this could be a big improvement upon current schemes that are known. I mean, to many ways, polar codes are practical in that the scaling of the complexity and so on is actually very good. The only problem is really the block length. Okay, so that brings me also actually fairly close to the end, I think. So if you're thinking about, again, gap to capacity now versus complexity, so this complexity bit, that's actually very good. Okay, so that's log 1 over delta. And that's probably as good as you might see this for, we don't really know what's happening for iterative codes, as I said beforehand. I wouldn't right now venture a guess, but that's very, very good in terms of complexity. So really, the only problem is length. Okay, so some open problems. As I said, variation on the theme that performs better for small block lengths. And then there are many small problems. For example, a lot of people have thought about do Ruediger codes, given that they're so close to polar codes and there are many nice connections. Would they achieve capacity? It's not that I guess we would think of putting them right now on a chip, but it's a long, nice classical set of codes. It would be nice to prove something about it. Make the scaling conjecture rigorous. Right now we talked about scaling versus the successive decoding. But it would, of course, also be nice to look at scaling on the map decoding. Now, we know that on the map decoding, the error exponent, I didn't mention that, but the error exponent is actually the same. Okay, so the error exponent doesn't change on the map decoding. We know from experiments that you can do a little bit better if you do map decoding. You can do this, for example, with the erasure channel. But the question is whether or not if that's enough. Okay, so let's assume you had polar codes and you found a way, rather than doing successive decoding, to do map decoding. My conjecture is that this would not really fundamentally change the way things scale, okay? But it would be nice to see whether that's true or not, because this might tell you whether or not in your construction you should just work on the decoder and see if you can do something, iterative and try to get closer to map, or if you really need some fundamental different way of constructing them. Okay, and then yeah, at that point, given that there's so many places where they work, it would almost be more interesting to find interesting non-contrived examples where they don't work, okay? Just because that might give you some intuition, maybe what you could change, what you could do, okay? So I mean this in a serious way. Almost any channel people have looked at, they work for source coding, they work for secrecy, they work for what you have not. So it would be almost interesting to find examples where they don't work, because that might tell you something that maybe you could still tweak in the construction and do in a different way. Okay, so assuming there was any message other than message passing, okay, in my talk. So if you really mostly I talked, of course, between iterative and polar codes. Iterative are still decodes to beat if it comes to put them in an actual chip. Okay, so there's no question, that they are currently for reasonable lengths by far the best codes. But there's still a lot, I think, of the theory missing. As I talked beforehand, I think we need to find ways of making this more accessible, making this much easier in the design, and somehow having easy and simple mechanisms that people can just use that don't necessarily have studied these codes to design them. Polar codes, on the other hand, are certainly one of the most beautiful constructions that you can think of. And they are essentially in every measure as much as you can hope for, except perhaps for one, which is exactly the block length. So if anyone would find a way to modify the construction, maybe expurgate this process in some way to have a better exponent so that you don't get 2 to the m, but maybe you get something slightly smaller to the m, this might make a big difference. Now, the other message is that I think in general, the scaling approach, okay, starting from looking at the capacity and block codes like Sergey and Yuli, and now what I talked about here with respect to the actual coding, I think this is still something where a lot of work could be done. I think it's a very useful approach. It has a very nice engineering interpretation, and in particular, it has lots and lots of open problems, because almost none, except for a few cases, almost none of the scaling things that I talked about are really currently completely proved, right? The only one really where we have a proof is for for iterative under the BC, and many other things are open. Okay, so thank you very much. That's it.
We certainly have time for some questions, so please feel free.
So in the example you showed, the first couple of channels were back channels, right? And we were sending the non-zero values on them. So why do we even send them? Why do we spend?
Okay, so I don't know. I could try to go back. I mean, this is a very small example, right? So I'm not sure. Okay, just say stop. I guess you had the demo, one of the.
It was a numerical example.
Yeah. So sorry. So maybe here. Yeah. So this is a very small example, and you would certainly never use a channel that has any of these Bhattacharya constants, but just to demonstrate it, right? You just say, I pick a certain rate I want, and then I pick the best ones and the worst ones, and I declare them fixed and frozen, and the other ones I use. You would certainly never use channels like this, right?
So we know that they reach capacity, right? Even for a large n, there might be a small subset of the first entries where they are bad channels.
Right.
So if I don't use them, don't I get overcapacity?
No, you can't. No. So that's exactly where the gap comes from, in that. So some of them will be clearly very good, some will be clearly very bad, but some will be somewhere in between. And those you will not be able to use in general. Okay, and this is exactly kind of what the scaling that I talked about is, exactly how many are in there, what's the exponent of those that are in there, because that tells you exactly how much you lose for a particular length compared to capacity. So those you would not use. If you would take all the channels and for each of them did coding on top, you would get exactly capacity if you did perfect coding, right? But now we simply say, no, we either do 0 and 1, and also, of course, and for this case, clearly you will lose something, right? But of course, also you have to be a little careful. We're talking about finite error probabilities, so potentially we might be actually slightly above, right? But it's not going to happen.
You mentioned about the threshold thing. So do you have some comments about the error flows for these cases?
Yeah, so they shouldn't have any, right? I mean, so they don't have an error exponent, but they have a very, I mean, it's e to the minus n is still very good, right? So you wouldn't expect there to see, you wouldn't expect the slope to change, right, for these codes. You wouldn't expect to see a curve like in the LBC setting, right? Because that means that there's some essentially constant-sized things that you have in there.
But then I have a question. So then why don't you do something like you are having some real good codes, and then you are having some very bad codes, and then you are having something in between. So can you do some sort of concatenation? So like if you can somehow identify those things.
Yeah, you could, but I guess the whole point is that you don't want to do, I mean, you could, but you don't really want to do coding on perhaps coding on top of the, oh, I see. So you're saying maybe for those one to get to bridge this gap. The question is then, maybe this is a little bit like maybe then in general concatenated construction, that essentially you then, this code then does all the work. So you might be to some degree back to square zero. But yes, maybe you could do something on top there, use some iterative code on top there, and so on. But the point is that if you do that, you lose somehow the nice elegance and provability, right? And then maybe you just should use an iterative code to start with, right?
So that in the simulation you have, these are in the other plot that you showed, you can predict the exact bounds of the performance for polar code, right? For finite block length.
You can, yeah, it's within the approximation, and again, there's no guaranteed error bounds, right? But within the scaling approach, you have some predictions, yes.
Also, the 10 to the minus 10 is from the scaling.
No. So the plots I showed were the exact things. Okay, so
They're not the simulation.
no. So because for the BC, you can just compute it, right?
Oh, but it's only for the ratio.
No, you can also do it for other ones, but it becomes computational complex. This applet will allow you to do it, but not up to a million. For the Gaussian, you can do maybe up to, I don't know how many thousand. It's a computational issue, right? It's not.
Use a polar code designed for a certain channel, say BC with a very Robin line, and actually you use it for a degraded version of the same channel. Say another range of channel is probably 6. Can you still get something out of it? Or
Sure, because as long as the channel family is degraded, it's perfectly fine, because it's easy to see that the choice of bits, the frozen ones, that obeys the degradation. So anything that's good for the worst channel is also good for the better channel.
yeah, but for the degraded case,
Oh, I see. You mean the upper, the other way around. Okay.
there will be some non-frozen bits.
Yeah. So then I think I think you.
Does this stop the
Yeah. I think it does, because all it takes is one guy, right, that comes in early, and that's a bad channel, and that will happen. Okay. So I think unless you do something smarter, then I think you will be immediately in trouble.
So, in order to pick up the good channel and the bad channel, you have to make all of these capacity calculations. When you have 10 billion calculation, is it too complex?
No, it's very easy. So practically speaking, it's not a problem, because the simplest way you can do it, just do decoding. Okay, it's essentially the same complexity as decoding, and you just need to decode for a long enough time. You have a good statistics, right? But theoretically speaking, you can do better. There's, for example, work by Alex Vardy and so on, where you can give strict upper and lower bounds under some computational models, and you can compute what the complexity of this is. There's also, in simplest case, it corresponds to dense evolution calculations. You can compute how many bits you need to, in precision, in order to have then a certain confidence on the results. So it's theoretically, I mean, practically speaking, it's not an issue. Theoretically, there are some algorithms that guarantee you certain things. And since you only do this once, maybe it takes a few hours for a code of 1 million, but it's not a big deal, right?
Just another question. This applies to binary input channel. So 0 and 1. So the idea can apply to.
Yeah, so one of the extension was non-binary, for example, that I mentioned. People have looked at non-binary case. This means also you can, if the channel is not symmetric, that you can now, using Gallagher's trick, you can also use the non-symmetric capacity. So there are extensions that people have looked at.
Okay, there are no other questions. This ends the lecture part of our, and let's give